Okay. Got to put all that smugly again. All right. Welcome to section 4.3. Welcome to quadratic functions. I'm going to do a click here just so I don't accidentally go backwards. Today what we're going to learn is we're going to take the generalized form of a quadratic function with two variable terms, x's in it, one squared, one to the first, and we are going to convert it into what we call standard form or vertex form. And the nice thing about this is that there's only one x term, which takes us back to our transformation rules. And when you're in this format, everything's a lot easier to do. Graphing, solving, everything's much easier. So to identify the vertex, it's the h and the k in this equation. And you'll notice that h is inside the parentheses as x minus h. And when you go to the point, it's a positive h. Again, that's an opposite effect of what's happening inside the function when we talked about our transformation rules. Remember, I also said, take whatever in the binomial, set it equal to 0, and solve it for x. X here would equal a positive h. And then the k on the outside, that's face value. So there's your k right there. Every parabola has an axis of symmetry that goes through this vertex. And since parabolas open up and down, this will be a vertical axis of symmetry. It's going to be a vertical line that flips over left and right. So that's going to come from your your x coordinate h. We're also going to identify max and mins, and if you recall, max and mins are y values. That's going to be the k. So what we're going to be doing is, for our graphing, is we're going to discover a pattern to graph your parabola using the vertex. And I'm going to give you a hint and this a value out in front, which happens to be, oh, by the way, the same as this a over here in the general form. And graphing this parabola, even though it's a curve, is going to be just as fast as graphing a line using the y-intercept and the slope. All right? So let's go discover the pattern. Here we have y equals x squared, our basic quadratic function. Its vertex will be at 0, 0. So if I put 0 in for x, 0 squared is 0, y equals 0, there's my point right there. Now, if I start going to positive x's, and I take these positive x's and I increase them by 1, like we were doing for that difference test. You want to see your x's increase at the same rate. So we're going to let them increase by 1. Take all those x values and let's square them. So 1 squared is 1, 2 squared is 4, 3 squared 9, 4 squared 16, 5 squared 25, 6 squared 36. So as I mentioned, all your x's increase by 1, but notice how the y's increase. This is where the pattern's going to be discovered. 0 to 1, increased by 1. From 1 to 4, increased by 3. 4 to 9, increased by 5. I'm beginning to notice, hey, wait a minute, these are all odd numbers. You don't think from 9 to 16, it's a 7. 16 to 25 is 9. 25 to 36 is 11. Yes, your y's increase by a sequence of odd numbers. 1, 3, 5, 7, 9, 11. So in fact, the next odd number would be 13. 13 plus 39, 13 plus 36 is 49, and that just happens to be 7 squared. Now, as I mentioned about that difference test, back when we were looking at linear equation data, do the difference test again on your y's. Take these differences and do the difference again. They all increase by 2. That's really important, because once that value is the same for your differences, that tells you the power on your x. So this is the first level difference test. This is the second level difference test. And since all these are 2's, boom, it's an x squared. If these numbers were different and I did the difference of those differences and it came out to be the same, that would be the third level difference test. Then it'd have to be an x cubed function. All right. So again, second level difference test makes it x squared. Now let's try another function. Y equals 3x squared. This pattern, I promise you, will be in every single quadratic function. It's never going to change. It might be altered, but it'll never change. So here I found the table for y equals 3x squared. I won't lie, I told you before. Remember when we did the piecewise functions? Yeah, I went and made a table off my calculator and copied down the numbers. I didn't crunch numbers. But my 0 through 6 is the same, counting by ones. Now let's examine the y's. 0 to 3 increased by 3. 3 to 12 increased by 9. 12 to 27 increased by 15. 27 to 48 increased by 21. 48 to 75 increased by 27. 75 to 108 increased by 33. That's not 1, 3, 5, 7, 9, 11. You lied. No, I didn't. What's the factors of 3? 3 times 1. What's the factors of 9? 3 times 3. The factors of 15? 3 times 5. Factors of 21? 3 times 7. Factors of 27. 3 times 9 and 33 is 3 times 11. There's your sequence of odd numbers right there. It's just that they've all been multiplied by 3. Wonder where that multiplication of 3 came from. Oh, right here, the A. Oh, yeah, that's right. That's our vertical stretch concept. Remember we said multiply all the y coordinates by 3 and you'll find the change. Okay, so if my pattern is 1, 3, 5, 7, 9, 11, then multiply your pattern by 3 to find all your points. And that will be your vertical stretch. So 1 times 3, 3. 4 times 3, 12. 9 times 3, 27. 16 times 3, 48. They're all a match. So if I take my pattern and multiply it by 3, I get the same numbers. So that's how we're using that transformation rule as part of our pattern. You can even have fractions. 0 through 6. Again, x is increased by 1. The points are 0, 1 half, 2, 9 halves, 8, 25 halves, 18. But notice how they increase. By 1 half, by 3 halves, by 5 halves, 7 halves, 9 halves, 11 halves. My 1, 3, 5, 7, 9 have all been multiplied by 1 half. So this is how we can use this pattern to plot points really, really fast. Now, you're going, wait a minute, what about the negatives? Don't worry about the negatives. When you square negatives, they become positives. Oh, it's going to be just like working with positive x's. So let's go ahead and graph our y equals x squared. Now that you've discovered this pattern, you're going to start with the vertex. That's like starting with the y-intercept. Then you're going to use your pattern, 1, 3, 5, 7, 9. And the fact, let's not forget, that your x coordinates always increase by 1. This is kind of like what I like to call my parabolic slope. I have my y-intercept, I have my slope. I graph a line really quick. For a parabola, I have my vertex, and I have my parabolic slope pattern. I can plot points. So here's how it works. Let's start with our vertex. 0, 0. All right, now remember the changes here. The x's always increased by 1. So that means I'm going to go from my vertex 1 squared to the right. My first odd number was a 1. Up 1, plot a point. Now from this new point that you just plotted, right from here, just like you were graphing a line, you do your slope again. Well, we're going to do our parabolic slope. We're going to go 1 to the right. And now we're going to go up the next odd number 3. Up 1, 2, 3 squares and plot a point. 1 to the right. Up the next odd number 5. 1, 2, 3, 4, 5. There's my point. From this point here, 1 to the right. Up 7. 1, 2, 3, 4, 5, 6, 7. There's my point. Let's see. 1 to the right, 9. Will it fit? 1, 2, 3, 4, 5, 6, 7. Nope, 9 doesn't fit. So I stop right here. So my curve of my parabola, I just connect those all together. And there's what we'll call the right half of the parabola. All right, now while we're here, because when I check your graphs that you make by hand, because you will have to make a graph by hand, when you draw this curve, notice that these points are on a column of squares, and they're like on the diagonal corners. So, for example, this part of the graph right here that I went up 5 squares, that red line should stay inside that column of squares until I get to that point. I should not go anywhere else. In this column of 7 squares, it's almost becoming like a straight line. The more the squares, the more a straight line. You can actually use a straight edge to connect them together, and it still looks like a curve. And what I want you to do here is just put the arrow at this endpoint right there. Don't try to keep going further up. I have seen so many people take their curve and it goes to the right too fast. And maybe they cross right here. You do that, I ding a point. Or their parabola starts to curve back in. Well, you don't want it to curve back in. It won't pass the vertical line test. It's no longer a parabola. I'll have to ding a point. All right, so we're going to stay connected to those corners on the diagonal corners of these columns of squares. Now here, my axis of symmetry is the y-axis. These points now fold over the axis of symmetry, which goes through my vertex. So this point being 1 to the right, flip it over, 1 to the left. Here I'm 2 to the right, flip it over, 2 to the left. 3 to the right, 3 to the left. 4 to the right, 4 to the left. And connect those up in the same fashion. All right? Again, there's your axis of symmetry, fold it over. So why can we graph parabolas really fast? It's because we're only graphing half of it. Once you have half of it, you fold it over that axis of symmetry line. And I don't mind if you put a dashed line, if you want, right through that vertex. That's fine. If you don't want to do the flip, 1 to the left up 1, 1 to the left up 3, 1 to the left up 5. You have the same pattern. All right, 3x squared. Now, we know what the points already are. We made the table, but this is how we graph it. This is the work you're going to do. We know that this 3 is going to change my sequence of odd numbers, 1, 3, 5, 7. So I'm going to multiply, write down 1, 3, 5, 7. I'm going to take that 3 and multiply it to all those numbers, and that's how my y's are going to change in my pattern. But my x's always increase by 1. So again, our vertex is at the origin, 0, 0. 1 to the right, up 3, plot a point. That's this 3 right here. 1 to the right, up 9. That's the second 9 right there, plot a point. I don't think 1 to the right, up 15 is going to work. Draw your graph. Again, long distances, use a straight edge. Get your ID out or something with a straight edge, or a credit card that you can send me your numbers. Some other straight edge. Flip it over the y-axis. Okay, that was my attempt at bad humor, so sorry. 1 to the left, 2 to the left, and there's my parabola. We can even work and graph fractions. Now, I'm going to promise you this. I am never, ever going to ask you to graph anything but a denominator of 2. I might put 3 halves, 5 halves, 1 half, but never a third, never a fourth, never a fifth. I'll show you why. Because you're going to take your 1, 3, 5, 7, and I put a 9 in here because I know I'm going to get a little extra space in here, and multiply it by a half. So that's really 1 half, 3 halves, 5 halves, 7 halves, 9 halves. Start at the origin, go 1 to the right, up half a square. We can cut squares in half. We can make that estimate. But thirds, fourths, and fifths, now we're getting crazy. From this point, we'll go 1 to the right, up 3 halves. And what I like to do is I'll put little tick marks here. I'll go 1 to the right, put a tick mark, and I'll put tick mark, tick mark, tick mark. 1, 2, 3 halves, plot a point. 1 to the right, put a tick mark. 1, 2, 3, 4, 5, put a point. 1 to the right, up 7 halves. 1, 2, 3, 4, 5, 6, 7. I like to put my tick marks. 1 to the right, up 9 halves. Draw my graph. Flip it over the y-axis. Right here, flip it over 2, 3, 4, 5. There's my graph. And again, notice compared to my original parabola, x squared, this is wider because I technically had a vertical shrink. I pushed my graph down a little bit as opposed to the 3x squared, which was a vertical stretch. Now, while we're here, I just want to make a mention about my math lab. When you're graphing, you might notice that, okay, I plotted my vertex and I want to graph my point. And I can't make the graph. All right, so here's what's going to happen. I'm going to go to my iPad here and I want to draw this out. So I'm going to bring it over here. And, oh, come on, get off this screen and come over here. Thank you very much. And let's say we're working with this 1/2 graph right here. So give me a second here to rearrange the stuff on my screen. And this will be very helpful. All right. Okay, so when you're in my math lab and you're graphing, and if you haven't graphed in my math lab or used it before, this will be helpful. You will see an icon that looks like this. It's a parabola-shaped icon with one point at the vertex. This is the first point you plot. Just like we're talking with our pattern. This is your second point. That's where you're going to go 1 to the right, up the A value. Whatever A is out in front. And the parabola in the program in my math lab, that's the only 2 points it needs, and it makes the whole picture for you. Now, the reason I'm stopping here at this graph to talk about this is because sometimes when you're graphing, and I'm going to kind of blow this up here, 1, 2, 1. You plot this point. All right, you move your cursor, you go 1 to the right, and you try to go up 1, and it jumps up to right here. You can't hit the halfway mark. That's okay. There's another pattern in parabolas. Notice when I go 2 to the right, I went up 1/2 and 3 halves. If I add those together, that's 4 halves. That's a 2. So if we look at our pattern here, 1/2, 3 halves, 5 halves, 7 halves, 9 halves, and I'm just going to put in 11 halves. If you add those pairs, I get 4 halves, 12 halves, 18 halves, which all can be reduced. 2, 6, 9. But the key is that's how far we're going up. But that's 2 to the right, up 2. 2 to the right, up 6. 2 to the right, up 9. So if they don't give us the ability to plot halfway on the grid, then this is how you can, this is your workaround. And again, this author they'll give you ugly fractions. They don't have any problem with ugly fractions. They might put a 1/3 out there. And again, you can't plot a third. You can't go 1 to the right, up a third. So you take your 1, 3, 5, 7, 9, 11 pattern, and we multiply them all by a third. And I'm not going to reduce anything here because I want to show you this. The pattern still is alive for finding whole numbers. Because the denominator is 3, now put them in groups of 3 and add these together. 1 plus 3 is 4 plus 5 is 9. That's a 3. Now, I just went 3 to the right, and I go up 3. 7 plus 9 plus 11. That's 27. That equals 9. That means I went 3 to the right again, up 9. And so that's how I can find nice points for plotting in my math lab. If I have a denominator of 4, then I have to add 4 fractions in a row. If I add those all together, 1 plus 3 is 4. 4 plus the 12, that's 16 over 4, and that's going to reduce and give you an integer, an easy point to plot. Okay, so I just wanted to point that out before we start working some examples. I know my video is getting a little long here, so I'm going to stop here and I'll build up a new video for our examples. All right.